Hey guys, today we're going to learn about exponential functions, going with section 4.1 in your book. So what makes something an exponential function? It's got to have that form b to the power f of x or y equals b to the power of x, where b is a positive constant. So in these cases like 2, 10, 3, a positive constant other than 1. And x can be any real number, 2 to the power of x, 10 to the power of x, 3 to the power of x plus 1. It doesn't matter if you put something up there, but it has that, again, that positive constant base. So over here in example 1, the exponential function, they give it to you, models the average amount spent in dollars at a shopping mall after X hours. So the longer you stay, the more you spend. What is the average amount spent to the nearest dollar after 3 hours? This is just having you plug it in. So we're going to type in 42.2 times 1.56, and x is the number of hours, so they told us 3. And you're going to type that in a calculator, and you're going to round it, and you're going to get about $160. So that's what this function is telling me, that I will probably spend around $160. Now, if you look in your graph, 3 hours, they told you $149. So did this function overestimate or underestimate? It definitely overestimated. So it overestimated, sorry, can't spell, by what, $11? So not much, but it did overestimate by $11. Moving on. Graphing. We're actually going to plug in some points here. So we're going to plug in x coordinates and get out our y coordinates. So let's do some negatives, 0, and some positives. Let's just see where it's going both ways. So let's start with 0. Anything to the power of 0 is 1. We'll do the easy ones. 1. 3 to the power of 1 is 3. 3 to the power of 2, 3 squared is 9. And then remember the negatives, all it should do is be a reciprocal. So 3 to the power of negative 1 is 1 over 3. Right? Instead of 3, it's 1 over 3. Instead of 9, it's 1 over 9. So let's graph. So we got 0, 1. We've got 1, 3. We've got 2, 9. I have to do open circles because it's not letting me put dots on here for some reason. It doesn't let me color in dots. And then we've got negative 1, a third, and you kind of just eyeball it. Oh, see, it doesn't like me doing dots. We'll get it on here somewhere. There we go. And then a ninth, so it's even smaller. And it's going to get smaller and smaller and smaller. So we're going to get really, really close, but understand there is absolutely no power. I missed. There is absolutely no power you can raise this to get 0. So we're going to get really, really close to 0, right? 1/9, 1/27, right? It's going to get really, 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 really tiny, but it's never actually going to touch 0. We call this line our horizontal asymptote. And it's the line y. I don't know why I put 2 e's. There's only 1 e. Y equals 0. So we know we're going to get really, really close to that line, but we're never actually going to cross it. So we're going to get really, really close, just never cross it. Now, this graph, 1/3, it's going to be the same things except for backwards. So when you plug in, let's plug in our same coordinates. Remember, 1/3 is the same as saying 3 to the negative x. So it kind of shows you this out here, but even if you didn't know that, 1/3 to the 0 is still 1. 1/3 to the 1 is 1/3. 1/3 squared is 1/9. So it's almost like they just flip-flopped, and then you have 3 and 9. So now we're at 0, 1, that stays. Negative 1, 3, so it looks like we're going the other way now. Negative 2, 9. And we kind of get it now, I hope. We're going to get really, really close to 0, but we're never actually going to touch that horizontal asymptote y equals 0. That's your horizontal asymptote. All right. Translations, reflections, everything still stands. Okay, if you see it on the end, right? So if you saw like 2 to the x plus 4, that graph is moving up 4. It's taking that 2 to the x graph and it's moving it up 4. If you see it up there with the x, like 2 to the x plus 1, or let's stick with 4s. 4, remember, think opposite. We're actually moving to the left 4. Reflections, we actually just saw one of those, right? We actually saw this one over the y-axis where, let me go back. You can see from here to here, this was a reflection. It took that 3 to the power of x and made it 3 to the power of negative x. It reflected, okay? It reflected over that y-axis. And then stretching or shrinking, if you see numbers bigger than 1, stretching, compressing, numbers between 0 and 1 are compressing. I don't know why they said shrinking. All right, so this one, I'm going to graph in 2 different colors here. So let's graph our 3 to the power of x. So 3 to the power of 0 is 1, 3 to the power of 1 is 3, 3 squared is 9. And again, we're going to get really, let's see if I can get this really close. But we're never actually going to hit 0. So now I'm going to grab a different color just so we see it. Let's grab red. This right here is telling me to move to the right 1. So it shouldn't affect my asymptote. I should still get really close to that y equals 0. I'm just going to take this whole graph and shift it right 1. So instead of 0, 1, I'm going to have 1, 1. Oops. 1, 1. Instead of, we're going to shift it right 1. Come on. And we're going to shift it right 1. So you should see that graph get really close to 0. Same concept. Okay, but we took that graph and shifted it right 1. So this one is our 3 to the x minus 1. All right, so this one we have a 2 to the x graph. So again, I'm going to graph that in purple. So 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. I think we got enough there. And again, we're going to get really close. We're going to get those fractional values, like 1/2, 1/4, 1/8. So now let's graph the transformation. So this right here is telling me to move it up 1. Now that will affect your horizontal asymptote. So right now my horizontal asymptote, let me draw that in purple, is y equals 0. Right? That's my horizontal asymptote. But when we shift up 1, your asymptote is going to shift up 1 as well. So now instead of being y equals 0, we're going to have a horizontal asymptote of y equals 1. So there's my new horizontal asymptote, y equals 1. And we're going to go ahead and shift our points up 1, up 1, up 1, up 1. So we're going to see, we're going to get really close to this, but we're never going to cross. So understand shifting up and down does affect your horizontal asymptote. That should shift up and down as well. All right. The next one, so you're going to learn about Euler's number. Very similar to pi, right? Pi is 3.14159. Your natural base E, that is Euler's number, it's 2.71. If you hit the button in your calculator, it gives you E. You should have a button E in your calculator. And I did post the calculator that I was using, so I did post a link to that. So you just use the button. It's non-repeating, non-terminating. It's just very similar to pi. So this is talking about this exponential function represents the gray wolf population, X years after 1978. If trends continue, we want to project the population in 2012, which already happened, but this book's a little out of date here. So we're going to type it in, 1066, and again, E is a button on your calculator, to the 0.042. And then X is your number of years after 1978. So from 1978 to 2012 is 34 years. And you're going to type this in your calculator. Again, I posted a link, and you should get 4,445.59, which we're going to round to 4,446 approximately. Should be our population of gray wolves in 2012 in the recovery area. All right. And our last example, again, you really, really, really want that calculator because it does all the work for you. So this is compound interest, talking about how much you invest, what the rate is, and how much you wind up with. So A is how much is in your account after so many years. Okay. So we're going to compound two different ways. So compounding per year, so you can have annually once a year, semi-annually twice a year, quarterly 4 times a year. You could have all different stuff here. Or you can have continuous compounding, which is definitely the better one. We like that one because you get more money. The more times you compound, the more money you're going to get. So let's take our principal, right? How much did we invest? 10,000. 1 plus my rate is always as a decimal, in decimal form. We don't want a percentage, we want a decimal, so 0.08. N is the number of times you compound per year, so this says quarterly, which would be 4 times in a year, and N times T, which is 5 years in this case. And you type this into your calculator. Let your calculator do the hard work. 14859.47. So that's nice. My $10,000 grew about almost $5,000, which is nice, in that 5-year period. Now let's see what continuous compounding will do. So we're going to use the different formula. Still your principal, so 10,000, E to the rate, again as a decimal, 0.08, times time, 5 years. And you're going to type this into your calculator as well. And we're going to get 14918.25. So it's not a huge difference, right? It's not a huge difference, less than $100. But I mean, you want that extra money. Continuously, the more times you compound, the more times you compound, the more money you're going to make. So if we went back and did this annually, we would not make as much money either. So the more times you compound, the more money you make. All right, that's it for today. Get the homework done.